Okay, this is 28th August, 2:16 p.m. my time, Pacific Standard Time. And so anyway, all I want to show right here is for the menu for the system here. Okay, channel 1. Let's see. Okay, channel 1 is set at DC coupling. Channel 2 right there is set for DC coupling. And channel 3 is set for DC coupling. So you can see that that color matches the channel that says channel 1, channel 2, channel 3, DC coupling. So all three channels are DC coupled, and you can see the numbers that the mean on the DC average for the blue shunt is the DC coupled DC average. This RMS number is not included in the data. That's only just for reference for tuning. And then the DC average for the timer shunt, that's DC coupled as well. And again, here's the menu, DC coupled, channel 2 is DC coupled, channel 3, channel 1, 2, and 3 are all DC coupled. So these numbers are DC coupled numbers, not AC coupling. And so anyway, for example right here, just for tuning reference, 489 RMS at the load shunt, and if I divide that by about, I don't know, 4.5 average right there, DC, that's a 108.66 times spread between that DC average and that RMS. And the waveform across the load looks pretty much like this. And I just changed it a little bit, decreased some of the gate resistance, but there's more below the line than above. But I'm not interested in proving that. I mean, visually it should be pretty obvious, but I'm only using these numbers to show it, of what this samples. So that's DC coupling. Now, one thing I want to show is temperatures. Okay, I just hooked up channel 4, which is the green line at the top, in reference to its own ground. It's also commonly grounded. I took the fourth one and I grounded it to the negative on the battery, and then the Tektronix channel 4 is to the top of the coil. So reference to common ground, where all 4 probes are common ground, then of course the RMS at the load is going to show an average voltage of 12.7, pretty close to what the battery voltage is going to be. So anyway, and those numbers right there for the load, and whether that's DC or AC on a load, is pretty much going to be right about the same if it's on the common ground. So anyway, this is I just tweaked the tuning a little bit. This is the waveform on the load. Pretty symmetrical above and below. Well, not too much, but that's even more symmetrical now. Had a little trigger covering up that ground there, but that ground really is halfway between. Okay, so anyway, that's just what I wanted to show is all 4 channels. All 4 channels are common ground. Yellow is to the front of the timer shunt, front of the load shunt. Battery voltage is purple, straight across the battery, and that's what common ground, straight to the top of the inductor. And electrically, the battery and the load positive are connected together, yet you're going to get it a little bit different if you have the probe actually on the battery terminal or on the exactly at the load, like I have right here, instead of the battery one right on the terminal. It does make a difference, but it's still common ground, so the references are all accurate. Celsius, for example, 19. I'm going to move it around, and then this is the resistor going between the battery positive and the diode that takes the positive input to the 555 timer. And that's how I'm varying how much power I'm letting to the timer. And so if I just go like this, you can see that's 8 and got up to, there's a spot of 28, 29 right there. So 9, and the ambient next to it is 19. That's 10 degrees Celsius above ambient. See, here's a resistor just sitting there, 19 on the table, and I can move around that resistor. This right here, this has been off for a little while. I've just been tuning the waveforms, so everything should be pretty much at ambient, at least on the surface. But the inside of this can vary a couple degrees while the outside is the same, because on the inside it's pretty protected environment. I mean, I could put some type of putty at the ends to keep any breeze from going in there, but it's more stable than the outside. But nevertheless, all these temperature readings are identical to the ambient. And when I say ambient, I mean ambient, not baseline. And just because these objects are metal does not mean it's going to be colder. Well, at least the wire there, you know, they could feel colder to the touch, but that's just because they're better conductors for heat. Now, one thing I'll show is this right here. This is sitting down on the ground, so this ambient down here is going to be about a degree lower. It's at a lower level, but everything in the box, 18 degrees. The point of this is just to show that just because you have these resistors and you got this metal and everything else, doesn't mean it's going to be below the ambient temperature. If everything is sitting long enough, it's all going to be the same temperature. And you can see that this timer chip, the 555 timer chip, is 25, gets up to 25 there, 25, and the board next to it is 19, so that's 6 degrees Celsius above. And again, this pot meter right here for the power to the 555 timer is 25, 24, let's see, 28, 29. That's 10 degrees above ambient. When I say ambient, I mean ambient. The MOSFET is running at room temperature. Okay, now you can see there's one degree above. Pretty much right there. And these pots right here. A little timer shunt. You see, everything is the same temperature. This right here is the same mass as this. It's the same environment, ceramic hollow core resistor, sitting side by side in the same ambient condition. So when I have the load temperature inside the load and I have the ambient probe inside of here, they're in the same environment, the same ambient, and so as the load temperature goes up or down, it's properly referenced to an ambient of the same environment, which is inside the control resistor with no power going to it. And so as the ambient changes, which it may fluctuate, this room only fluctuates maybe 2 degrees, maybe 3 at the most, over a 24-hour period right now in late August. When it's 100 degrees outside, it's between 19 and 23, 24 Celsius, whatever Fahrenheit that is. So anyway, and as the ambient changes, the important thing is that the load, whether it's above or below ambient, stays a consistent margin. So if ambient goes up 2 degrees and this is at equilibrium, the load, for whatever the circuit is powering it, it's going to stay the same temperature above ambient. As the ambient goes up, the load goes up, or if it's cooler and the ambient changes, this will follow by that same margin.